So you guys, we are going to do the mean and the standard deviation today for a discrete random variable. All right, so again, a discrete random variable is when you have a table, so there's like space or gaps in between, all right? And the mean formula is on the AP exam, all right? So write this down. This is mu of x. So this means the mean of your random variable x. So like yesterday, x, the random variable we did, was the number of heads when you flip a coin 3 times. All right. This is another way to write the mean. E of x means the expected value, which just means the mean, okay? So to find the mean when you have a table, you do the value times its probability, plus the next value times its probability, plus the next value times its probability, all the way to the end of the table, all right? So you just multiply and add. Okay, this Riemann sum, you guys, is what's on there. It just means you add up each data point times each of their probabilities, all right? All right, so remember our APGAR score that we had the other day for babies. So everybody gets a score. You either get a 0 through a 10, all right, on like how healthy you are. All right, X is just a randomly chosen baby and what their APGAR score is. So it says compute the mean and then interpret this value. So you can either write mu of X or E of X, all right? And then you're going to do this times this. 0 times 0.001 plus this times this, 1 times 0.006. No, you don't. And then I'll do one more just for fun, all right? And then you can write plus dot, dot, dot. All right. Okay, so if you were to plug all that in, you get 8.128. It does say to interpret this. Okay, remember we learned that probability is a long run probability. So this is after many, many, many babies are born, all right? The average APGAR score is 8.128 for a randomly chosen baby, all right? So it's a long run probability that you want to describe after many, many babies. Okay, let's do standard deviation. All right, standard deviation is what it used to be. It's our typical distance from the mean. It's like means the same thing, right? So if we have an average APGAR score of 1.28, then we want to say how much are we typically off by? Oh, I forgot to say, you guys, do not round this number to 8, okay? Never round because, yes, you can never actually get, notice that a baby can only get like an 8 or a 9 or a 10, right? It's discrete. But this is a long run probability, so they need you to understand not to round because it's a long run probability after many, many babies are born. All right, so don't round these, that's all. All right, so our standard deviation comes from variance, or they're related. If you remember, variance is the standard deviation squared, and the standard deviation is the square root of the variance, okay? So var x just means variance. And yes, you need to know this notation, okay? Sigma squared x, okay, is the variance. If there's no square on it, it's the standard deviation. So we're going to do the first data point in the table, okay, minus the mean that we just found. All right, so you will have already calculated the mean, most likely. If not, you're going to want to calculate it, all right? So minus the mean. And then you square it, because we're doing a typical distance from the mean. So we don't want any negatives, okay? And we multiply by its probability, okay? The first data point's probability. Then you do the next one. So the next data point minus the mean squared times its probability, et cetera, et cetera. All right, keep going. The standard deviation is the same thing, but with the square root. So notice it's sigma x. This is the formula that is on the AP exam. All right, this one here. So it is just telling you the square root of every single data point minus the mean squared times their probabilities, okay? So it's the exact same formula, but with a big square root over the whole thing. All right? Go back. Sorry. Too fast. By the way, you guys, here's the formula sheet. Right underneath the two that we just learned for chapter 5, okay, these two up here, this entire box is what we're doing for chapter 6. These two are the ones we just did. The mean and standard deviation right here, it says discrete random variable. All right. Basically, if you have a table, this is what you do, okay? If you see a table, do your mean and standard deviation like this. All right, so let's do the standard deviation for our baby scores. All right, so first we're going to start with sigma x, which means standard deviation. All right, we're going to do a big square root. Okay, we start with our first data point, which is 0. We subtract the mean that we just got. I would write one of these down, you guys, and square it. And we multiply by its probability, 0.001 plus. Okay, then we're going to do the next data point, which is a 1 minus the mean squared times its probability, 0.006 plus. I'm running out of room, so I'll just do my dot, dot, dots, okay? And we get like, I think this one is 0.94. Let me look. JK, 1.437. Now you're going to want to interpret this. Usually I interpret them together, right? So in the long run, after many babies are born, the average APGAR score is 8.128. This number here is what we're typically off by, all right? And we're typically off by a score of 1.437. Okay, I don't think you need to write this down because we've like done this a lot, but let me just explain continuous again. All right, so discrete has spaces or gaps in between. Okay, continuous means like you could get a score of 3.9999999. Now in the last problem you couldn't, right? You either got a 3 or a 4. But in continuous you could get 3.99999, right? So x, the variable, takes all values in an interval of numbers, okay? The probability distribution of x is described by a density curve. Which density curve are we usually going to use? Yeah, normal, all right? We're usually using the normal curve. They will tell you, for now, that it's normally distributed, all right? The probability of any event is the area under the density curve and above the values of x that make up the event. So like shade your curve for whatever it's talking about and do a little norm CDF, right? Here's one that's not normal, all right? If it's not normal, they'll probably provide a picture for you like this, okay? How do we find probabilities of events like, okay, so what does this say? The probability that y is in between 0.3 and 0.7. If you have a density curve, I don't know that you can call that a curve, but whatever, all right, that looks like this, we're just basically finding area of a rectangle, okay? So it's not hard, all right? What I'm going to do is, what is this distance from 0.3 to 0.7? Exactly, it is 0.4. It's telling me here that the height is 1. So the area is base times height. 0.4 times 1 is 0.4. All right, so you might have one like that you just do area under the curve from there to there. But more than likely, you'll have a lot of these, okay? So here we have the heights of young women, okay? It tells us that it follows the normal distribution. For now, every single problem will probably tell you that. Eventually, we're going to figure out how to know whether it's normal or not. But for now, they're going to tell us. All right, so what's the probability that a randomly chosen young woman has height between 68 and 70? I think it told us right here, okay, choose one young woman at random, call her height y. So y is the probability of choosing a random person, woman, okay, between this height. So for my probability statement, I would write it like this. Okay, between 68 and 70. By the way, are those the same? Yep. In a continuous distribution, that means the exact same thing because like 68 has no actual area under the curve, okay? In a discrete distribution, these are totally different, okay? Discrete, the table, it definitely means something different. So pay attention if it's discrete. Continuous, it doesn't matter which way you do it, all right? So anyways, it says that the average height is 64 of these lovely young women, and then 2.7 is the standard deviation. So in case you guys forgot, you add that 2.7 like 3 times, so whatever that is, and you could subtract it 3 times. You guys remember that? All right, and then we're just going to shade like 68 to 70. I'll pretend like it's there to there, okay? So that's the area under the curve. So since it's normal, we just do norm CDF. My lower bound in this problem is 68. My upper bound in this problem is 70. The mean was given to me above, 64. The standard deviation was provided above. It was 2.7. Okay, and my final answer is 0.056. Okay, so my chances of randomly choosing a woman and finding that they're between 68 and 70 inches tall is 5.6%. Right? Okay, we are going to do this one on the calculator just to show you guys how to check mean and standard deviation for a discrete random variable. This is discrete because it's a table, so we're going to plug it in. So everybody grab a calculator. All right, you guys, go to add lists and spreadsheets, or go to your like lovely spreadsheets, okay? All right. So this problem is a number of cars sold during the first hour of business on a randomly selected Friday. Okay, so it's number of cars sold within the first hour on a Friday. So we're plugging in the number of cars sold, 0, 1, 2, 3. So you're going to title your first column here, cars. Okay, and the second one is probability. So I'm plugging in what the table says, 0.3, 0.4, 0.2, 0.1. Bless you. Okay, remember when we did one variable statistics for one list of data? Okay, it's very similar to that. You just have one extra step. So we're going to go to menu. Then we're going to go to statistics. Then we're going to go to stat calculations. Okay, we are still going to go to one variable statistics. Okay, do not use two variable statistics in this class. All right, always use one variable statistics. So I click on that. Also, don't change the number of lists, which seems weird. I know we have 2 columns, but leave it as 1, all right? It's one variable. So then my X variable is cars, and this is the one new thing you have to plug in. Where it says frequency list, you need to put probability. We used to just put 1 there for everything, right? It would just be like they're all the same amount, right? This one, though, every single value takes a probability, so you need that. And that's the only additional thing, all right? Then you press OK. All right, so there's the mean. We used to use S sub x. That's what you should mostly use, all right? But it doesn't have it. We're going to use sigma x on this one. So that means that on average, okay, in the first hour of business on any randomly chosen Friday, after many, many Fridays, they sell 1.1 cars, okay, in the long run. And this is how many cars we're typically off by, all right? Again, make sure you don't round those too far. I mean, round them to like a certain decimal, but do a decimal place. Okay, so compute and interpret, that's all you're doing. I would like to see the formula. Again, make sure you at least start the formula mu of x equals 0 times 0.3 plus 1 times 0.4 plus ... And sigma of x, be sure you do your big square root and do 0 minus the mean squared times its probability plus at least 2 of them, all right, minus the mean squared times its probability ... Okay? So at least show me the start of those formulas. All right, you guys, go ahead and try 6.1b. All right, you guys, a couple things I'm going to count off for. So please check that you actually did this. All right. On this lovely histogram, make sure you actually labeled your axes. Lots of people forget that. I will count off if you did not label your axes. All right, on this next one, you need to make sure you labeled correctly either mu of y or e of y for the mean, okay? Show at least the first two, and then that you got 2.076. All right, for the standard deviation, be sure you have sigma y, and then your start of your formula, I should see at least two of these, and then dot, dot, dot. So you should have 0 minus the mean squared times 0.155. And then 1 minus the mean squared times 0.195, dot, dot, dot. And you get 1.318. All right, then make sure you interpreted in the long run, all right, after many, many games, we would expect the average number of goals per game to be 2.076. And then we're typically off by about 1.318 goals. Okay. For your norm CDF, you guys, a lot of people miss this. I'm counting off if you didn't put the P of right here. Some people are like not remembering your less thans and greater thans, you guys. What does this symbol mean? Yeah, it's like it makes an L for less than, okay? As long as you put your X on the left, then this makes an L. X is less than 31, all right? Normal CDF, you need to label each part, right? Lower bound. Yes, you can put 0. I always just do negative, a big number, all right? Upper bound 31, mean of 34, standard deviation of 3.5, so you get about 20% or 19.6 or something, all right? That a randomly selected, you don't have to write the whole sentence, but that's what that means, that a randomly selected toddler weighs less than 31 pounds, all right? All right, you guys.